In this video, we're going to be going over some simple harmonic motion practice problems. So a platform of mass 2.0 kilograms rests on a vertical spring with a spring constant K is equal to 250 newtons per meter, as shown on the left. The equilibrium length of the spring is L1. A ball of clay of mass 0.5 kilograms is then placed on the platform and the system is allowed to come to rest, as shown on the right. The new equilibrium length of the string is L2. What is the difference, L1 minus L2, between the equilibrium lengths of the string? Okay, so what we need to do is we have to find L1 minus L2. So we need to understand what the equilibrium of a spring is. So we know that F of the spring at equilibrium is going to equal to the F of gravity. And we know that from Hooke's law that F of S is equal to Kx. And we know that from FBD, if you have a block and you draw the FBD for it, it's just going to be mg, mass times gravity, is going to be the force, and you have Fs acting upward. So you can replace that with mg. Now, after that, you are going to solve for x by dividing both sides by k. And you have x is equal to mg over k. So that is going to be what your compression is. Now, we don't just want that algebraic form. We want to actually plug it in. So we know what the mass is. So that's m. And we know what g is. And we know what k is here. So now let's plug all that in, and you're going to have x is equal to 0.5 times 9.8 divided by 250, and that's going to equal to 0.02 m when you plug that into your calculator, and then that's going to be option A. So now let's move on to the next question. A block of mass m oscillates on a spring with frequency f. Which of the following expressions is equal to the spring constant of the spring? So for this question, we know that we have a mass spring system. And for mass spring systems, you have a formula that is F is equal to 1 over 2 pi times the root of K over M. So with this starting equation, what we want to do is we want to solve for what K is. So if we multiply both sides by 2 pi, and then after that, we simplify. So this is going to be canceled out. You can cancel out that 2 pi. Here you're going to have 2 pi f. And that's equal to the root of k over m. But we don't want it to be k over m. We want it to be just what k is. So you're going to square both sides. And then you're going to get 2 pi f squared is equal to k over m. After this, you're quickly going to, you can square that. So that's going to be 4 pi f. And that's going to be pi squared, and that's going to be f squared. And then you're going to have k over m. But what you want is just what k is. So you can multiply that by 1 over k. So that cancels out. And you're going to have 1 over m is equal to 4 pi squared f squared over k. But what you want is not what 1 over m is. You want what m is. So you can multiply both sides by m. And, oh, what we wanted to do here was get k. Well, I don't know why. Should not have divided by k there. So, okay, what you do here is you're going to multiply both sides by m, right? My bad. So that's going to be that, and you're going to have k is equal to 4 pi squared mf squared. So that's going to be your answer. And which one does that match? That matches option D. So a block is attached to a horizontal spring. The block is held so the spring is stretched and the block is released from rest, undergoing simple harmonic motion with a frequency of 2 Hz. How long after release will the block first reach a point where it's momentarily at rest? So we know that F is equal to 2 Hz, and we know that it's stretched and released from rest. And it's released from rest. We want to know how long until it's momentarily at rest again. So first we have to find what the period is. So if we know what the frequency is, we know that frequency is equal to 1 over t. So that means that t, if you solve for t, you just multiply both sides by t, and then that cancels, and you divide both sides by f, and t is equal to 1 over f. They're essentially, these two are reciprocals of one another, so you can just flip the fraction as well to find the other one. So that means that t is equal to 1 over 2, because f is equal to 2 hertz, so that's just a reciprocal, and that's going to be 0.5 seconds. Now, our second step is to find when it's momentarily at rest. Therefore, we have to find when velocity equals to 0 again. So we're finding when does v equals to 0 again. And when you have simple harmonic motion, you're going to have v equal to 0 at the end points of your spring motion. So when you have your string like this and you stretch it, whenever you're at the end points, that's going to be when you are at your amplitudes, aka you're at plus or minus a. So that means that what we had originally was that the starting stretch means that the block begins at one end point. Block starts at one endpoint, and then after that, that means that the next time it's at rest, next time it's at rest is at the opposite endpoint. Therefore, this occurs at half a period. This is half a period, so that's going to look like this. You're going to have t is equal to t over 2. So now you have to actually calculate that. So you know that t, your time, what you want to find, when does this happen, right? T. So what was your period again? Your period was 0.5, which we just found, and you have to divide that by 2. So you're going to have 0.25 seconds as your time. And let's just circle that as an option. So 0.25 seconds, that is going to be option A. Now, for our next question, we have an object with a mass m attached to a horizontal spring with a spring constant k undergoes simple harmonic motion with an amplitude a and a period of t, which of the following expressions is equal to the maximum speed of the block. So when we know that the maximum speed, this is going to occur at the equilibrium point. That's when your v max is equal to amplitude omega, and this is true. So we know that two equivalent forms of this equation is going to exist because omega is equal to 2 pi over t, right? And we know that that's for a period, and we know that for a mass spring system, you're going to have that omega is equal to the root of k over m. So now that you know that, you can take your omega and you can sub that into your equation. So you know that v max is equal to a over k over m. So after that, that's going to be what your a is. So where do we have that? We're going to have that as a over k over m. That's going to be option B. So for our next question, we have a block is attached to a spring. A block attached to a spring is held at position x equals 0 and is released. The block then undergoes a simple harmonic motion along the x-axis. The force exerted on the block by the spring is a function of the block's position x is represented by the graph. Which of the following positions, if any, corresponds to the equilibrium position of the spring block system? So we have a force versus position graph. This is your force, that's your x position, and we know that for the EQM, the equilibrium of a spring block system, you're going to have that your summation of forces is equal to 0. So your EQM position is where the force graph crosses 0. So if you look at the graph, at x is equal to 0, we can see that we're at 40 newtons, and then we can see that the force is going to decrease linearly. And we see that the line crosses at f is equal to the line crosses f equals 0, this x-axis at 0.5 meters. So that means that with our interpretation that when f is equal to 0, aka when we're touching this x-axis, This is when you have no net force. No net force. And that means that the block is at equilibrium. So that means you're at EQM. Therefore, you're literally just looking for where is the intersection of the line with the x-axis, aka option B. Now, for your next question, you have a simple pendulum near the surface of Earth has a period of TE. The same pendulum is transported to the surface of the moon, where the acceleration due to gravity is approximately g divided by 6, and the pendulum has a period of Tm. The ratio of Tm to Te is most nearly what? So for this, you're going to have to use some proportional reasoning. So we know that on the moon, we're going to have a gravity of a sixth of the Earth. So what we want to find is this ratio right here, Tm to Te. So Tm over Te. Now, we're going to use what the period formula is. So we know that T, for a pendulum, we want to find the pendulum period. So we're going to label that T of a pendulum, or you can also write that Tp, and that's going to be 2 pi, the root of L over G, the length of the string divided by your gravitational constant G. So this comes from your small angle motion equation. And from this, what we can clearly see is we can see a proportional relationship. So we can see that T is in the numerator, and we can see that G is in the denominator, but it's also underneath a square root. A square root. So that means that if you have T, that's going to be proportional to 1 over the root of G if you're not examining anything else and then any other of the constants or the other variables. We just want to look at the relationship right now between these two variables. So now all you're going to do is you're going to find those two ratios, and you're going to just substitute them in the top and the bottom. So you're going to have 2 pi for Tm. You're going to have 2 pi over L over G over 6. And you're going to have, for Te, you're going to have 2 pi over the root of L over G for Te. So now, after this, you're just looking at what the difference is. And the reason why that's G over 6 is because basically you're just taking your G. These are both your G's, but your G over 6 here is different. So you're always going to plug in G there. But here, for the moon, that is a sixth of it. But for the Earth, that is just the normal one. That is the reference of what we're comparing it to. So it's just still going to be G. So that's the reason why. Now, for specifically, if we analyze this, you have Tm is equal to, you can factor out the root 6, and then that will just leave you with 2 pi over L over G. So therefore, you can see that the only thing that is left over when you are looking at this is simply going to be that root 6. So that means that you can see that the ratio is going to be root 6. And you can see that that's in the numerator. So that means it's going to be root 6 to 1 because it's root 6 over 1. So that means our answer is going to be option C. Now, for our next question, we have at time t is equal to 0, an object is released from rest at position x is equal to positive x max and undergoes simple harmonic motion along the x-axis about the equilibrium position of x is equal to 0. The period of oscillation of the object is equal to t. Which of the following expressions is equal to the object's position at time is equal to t over 8? So what we know is that at t is equal to 0, it's released from rest, and our starting position is x is equal to positive x max. So what that means is you are at your max displacement. And now we have to write what our simple harmonic motion equation is. So our general position equation is going to be x of t is equal to a cosine omega t. And this form is used when the object starts at max displacement. So in this case, a is equal to your x max. Now, what is our angular frequency? Omega. So omega is equal to 2 pi divided by t. Now, you're going to solve that, you set that in, so you have x of t is equal to x max for your a, and you have cosine 2 pi over t times time still. Now we are going to evaluate at t is equal to t over 8. So what that means is you're just going to substitute in. Now, where's t? Here. You're just going to substitute that in. You're going to, x of t is equal to x max cosine 2 pi over t times t over 8. And this is going to be equal to x is x max cosine 2 pi over 8. And this is equal to x of t. This is going to be x max cosine pi over 4 if you just simplify that fraction. So that's going to be your solution for this question, and that's going to be option D. Now, for our next problem, we have a block of mass 0.5 kilograms is attached to a horizontal spring with a spring constant of 150 newtons per meter. Now, the block is released from rest at position x is equal to 0.05 as shown and undergoes simple harmonic motion, reaching a maximum position of x is equal to 0.1 meters. Now, the speed of the block when it passes through the position x is equal to 0.09 meters is most nearly what? So, again, that's our mass. This is our k. We're released from here. Your max position is 0.1, and your speed is that. So, what we're going to do is there's no friction mentioned, nor air resistance, so what we can assume is that we have conservation of energy. And a lot of these questions types, they're usually going to ask you for something where you have to identify that conservation of energy is applicable. So you have to check if those conditions are met. You don't have any friction, you don't have any external forces, and you can declare your conservation of energy. And then you can compare your initial and your final energies. So you can solve for whatever you need. So our total energy is constant. Therefore, we say E initial is equal to EF, and energy is equal to 1/2 KA squared. And finally, we have 1/2 KX squared plus 1/2 MV squared. This is at position X. Now, if we set them equal, we can multiply both sides by 2. And this is just going to be KA squared is equal to KX squared plus MV squared. Now, if we solve for velocity, that's going to be MV squared is equal to KA squared minus X squared. And this is going to be V squared is equal to K over M, because you have to divide that by M because you want to just isolate V. And that's going to be a squared minus x squared. So now after that, you just take the root of both sides, and that's going to be v is equal to k over m root of all that. And that's going to be a squared minus x squared. And now all you have to do here is we want what the speed is. So we're given all these values. We can just plug these in. So for mass, we have 0.5 k. Okay, so v is going to be equal to 150 over 0.5 0.10 squared minus 0.09 squared. And now after this, if you plug this into your calculator, which you'll have for this question, is going to be 0.75 meters per second. And we can see that's option D. Now for our next question, we are going to have, in figure 1, a block of mass m compresses a spring with spring constant k, a distance delta x as shown. The block is then released, and then immediately after rest, the acceleration of the block is a1. In the figure 2, a block of mass 2m compresses a spring with a spring constant 2k, a distance of delta x as shown below. The block is then released, and immediately after rest, the acceleration of the block is a2. Which of the following correctly compares a2 to a1? So we know in figure 1, again, this is our mass m. We have k labeled for us. We have delta x. So we want to compare in these two figures what is the acceleration immediately after rest. So immediately after rest. So we're going to use Hooke's law. So Hooke's law states that F is equal to kx, And we know that F is equal to MA, and we can rearrange that for A is equal to F over M. So now in system 1, let's compare what these are for both. Now here we can see that we have F1 is equal to K delta X, and your A1 is equal to K delta X over M. Here we have F2 is equal to 2K delta X, and our mass is 2M. So A2 is equal to 2K delta X divided by 2M. Now, if you simplify this, that 2 cancels out, and you're just going to have K delta X over M, A2. So what you have here is that A2 is equal to A1. And this makes sense because also if you look at the formula for what your acceleration is, it doesn't, it just cancels out here. You can see that that 2 cancels out, so that's why it doesn't matter. So our answer is going to be that they're equal to each other. Now for question 10, a block is attached to one end of a horizontal spring. The block is displaced by a distance delta x from the equilibrium, and when the block is released, it oscillates in simple harmonic motion with a period of t. If the block is displaced by a distance of 2 times delta x, it will oscillate in simple harmonic motion with a period of t. Why does the period not increase when the initial displacement increases? So let's write what we just read. So block displaced delta x, then you have a period of t. Now again, if you have a block and it's displaced by 2 delta x, that means your period is still going to be equal to t. Now let's look at what the period formula is for spring motion. So when you have spring motion, you're going to have that t is equal to 2 pi times the root of m over k. And what we can see here is that there is no amplitude inside of this equation. Therefore, t doesn't depend on amplitude. So that means that what our amplitude, it only affects our speed and our distance, not period, because it's not in the equation. Now, if we look at the explanations, we can see here that when we have a correct explanation, we need to see that that a large displacement is equal to a larger distance, right? And also, we need to see that during this, the speed stays the same, or the speed increases, proportionally. So the time stays the same. So what we know is that if your displacement doubles, that means that your distance traveled also doubles. And also your speed is going to double. Your speed doubles. So that means that t, you know that t is equal to your distance over your speed, right? And that's going to remain the same. Remains same. So let's look at our options. Because even though the block travels a larger distance during one oscillation, when the initial displacement is greater, the average speed also increases by the same factor. So that's going to be option D for this question. Now, let's go on to our next question. Question 11. So, System 1 and System 2 of each block consists of a block attached to a compressed horizontal spring as shown. In both systems, the spring is compressed by the same distance and the block is released from rest, undergoing simple harmonic motion. In the period of block in System 1 is T1, and the period of System 2 is T2, where T1, the period of T1 is greater than the period of T2. The block of in system 1 takes time t1 max to reach its maximum speed, v1 max, and the block in system 2 takes t2 max to reach its maximum speed, v2 max. Which of the following correctly compares t1 max to t2 max and v1 max to v2 max? Okay, so for this problem, we can remember again this situation. So we need to first look at the time to reach the max speed. So here in the time to reach the max speed, we know that the max speed, it happens when you're at the equilibrium. So if you start from max compression, and that means that your EQM occurs 1/4 of the period. So that means your T max is equal to T over 4. So if we look at T1 and is greater than T2, that means that T1 max has to be greater than T2 max. Now, if we look at the maximum speed comparisons, we're going to see that the maximum speed formula Vmax is equal to amplitude times omega, and omega is 2 pi over t. So that means Vmax is equal to 2 pi a over t. And since T1 is greater than T2, that means that your V1 max has to be greater than V2 max. And you can look at that because of the fact that T is going to be in the denominator. So when T is larger, we're given what T was. So if T is larger for one of them, that means that T is going to divide that 2 pi a, and that's going to create a smaller number because it's in the denominator, and when you divide it, it's just going to be a smaller decimal compared to the other one. Therefore, it's going to be a flipped sign. Therefore, these two are going to be opposite. So now, which one of these matches are what we have? So that's going to be the last one. T1 max is greater than T2 max, and also V1 max is greater than V2 max. So let's see here. V1 max, V2 max. Wait, let's see here. Or hold on. Which one is this match? V1, V2 is greater. So let's see here. That would be C. Let's just start this. So now for this next problem, we have 12. 2 blocks are attached to a horizontal spring, and they start with the same spring potential energy. The blocks are released at time t is equal to 0, and the first to reach their respective maximum displacements at time t is equal to 1 seconds, as shown in the figure. At time is equal to t is equal to 1 second. The block on the left has a larger displacement from its point of release than the block on the right. Which of the following correctly compares the masses of the blocks? So we know they start with the same spring potential energy. So what that means is that you have that U is equal to 1/2 kx squared, and your max displacement is t is equal to 1 seconds. So that means that your left displacement, and you say you have that your left has a larger displacement. So let's look at the time to reach the max displacements. So max displacement is this. Max displacement. That's going to be when you have t is equal to t over 4. And thus you have that t is equal to 4 seconds if you just multiply both sides. And that means that both periods have the same period. Both systems have the same period. Systems. And what's our period formula? It's t is equal to 2 pi times the root of m over k. Now, if your periods are equal, so if t periods are equal, what that means is that you have m1 over k1 is equal to m2 over k2. You can set those equal. So now, after you do this, you're going to do your energy equation. So we know that they both start with the same potential energy. So that means you can say US1 is equal to US2. So you have 1/2 k1 x1 2 is equal to 1/2 k2 x2 squared. Now just cancel out that 1/2 to simplify things, and you have k1 x1 2 k2 x2 squared. And we know that given that your x1 is going to be greater than your x2, that means that your k1 has to be less than your k2, because you can see that both of these are going to be summing to the same value, or their products of these two values are the same. So when you have one thing and you increase the other, okay, you increase one thing, you have to decrease the other in order to get the same number. So if you have 6 times 4, for example, like if you have 6 times 4, that's equal to 24. But now let's say we make the first number equal to 4. How do we still make it equal to 24? We still have to multiply it by 6, because we have to increase the second number to compensate for the deficit in the first number. And the same thing works here algebraically. When you have this situation like this, when you have conservation, or you have things that are set equal to each other, you need to compensate for the deficit in the other variable by increasing the other one, because of that direct relationship. You can see that so it's actually not direct, they're inversely related, because it's multiplication. When you have multiplication, that's inverse relationship. Okay, so now for our next problem, we have 13. So let's actually mark what this was here. So this is going to be your answer option of A. So let's see here. This is going to be A. Now for our next problem, we are going to have that a block is released from rest on a track that consists of 2 ramps that are at the same small angle to the horizontal as shown. The block makes a smooth transition from one ramp to another, and the friction between the block and the track is negligible. The block slides back and forth along the track. Will the block undergo simple harmonic motion? Why or why not? So in this question, we need to know what simple harmonic motion is. So when you have this, it means you have to meet this certain requirement of a restoring force, Fs, or Fr, and it must satisfy this condition, which is Hooke's law. It must satisfy Hooke's law. And Hooke's law is just F is equal to negative kx. And this means that your force, that negative sign means that the force must point toward the equilibrium, the EQM. And also that your force, it has to be proportional to your displacement. As you can see in this problem, we can see that F and K are both in the numerator, and we can see that they're directly related. So if we look at the force on the ramp and we draw the FBD for this diagram, you can see that you have pointing up is going to be your normal force, and pointing down is going to be your force of gravity. Now, if you dissolve your FG, because of the fact that this is on an incline, it's going to be a small angle incline, but nonetheless, there's still an angle theta right there. Therefore, you have to break this down into components. Now, what you see is that the incline force on the ramp is going to be F incline force along the ramp. Not necessarily this color, but you're going to have to break that up like this. So you have a force like that, and you have a force like this. So actually, let's make this a little bit straighter. And this is going to equal to mg sine of theta. And since we know that the ramp angle is going to be constant, therefore you can say, because it's going to be constant, because if you can remember again, if you have an angle like this, any angle, all of these, that's going to be the same theta. If you have an angle, it's always going to be the same, because you could just draw the angle marking at any distance r from the center, and it would still be the same theta. So because that angle is going to be constant, you can just say that your force is going to be constant, because your force is dependent on mass times the gravity, and gravity is going to be constant, your mass is going to be the same, and your angle is going to be the same as well. So sine of theta is going to output the same number every single time. So it's going to be a constant force. Now let's compare with our simple harmonic motion requirement again. So F here is also going to be proportional to X, your displacement, aka another way to write that. And your F is going to be constant. But here, that does not depend on displacement. It doesn't depend on displacement because it's always going to be the same no matter what your displacement is. So that means that your motion is not sinusoidal. It's not going to be sinusoidal because it's not proportional. Because it would always be the same. That's because the restoring force parallel to the ramp. So what we're talking about is that restoring force. So that's going to be this force right here. It's parallel to the ramp. Is not proportional to displacement. So this is going to be option D. Now for our next question, you are going to have some graphs. Now the graph shown in figure 1 represents the position x as a function of time for an object of mass m oscillating along the x-axis while attached to a horizontal spring. Which of the following graphs could represent a position time graph of the object of mass 4m attached to the same spring and oscillating with half the amplitude of the original object? Okay, so for this question, what we are going to look at is what the period is proportional to. So TSP is equal to 2 pi over the root of m over k. So what we can see here is that if you increase your mass, increase m by a factor of 4, that means that it will increase your period by a factor of 2. So that means that your OG period, your T original, was equal to 0.5 seconds. That means that you should have a, here you had that at T is equal to 1 seconds. Yes. So the original period was 0.5 seconds, and the graph indicates this with a period of 1 second. So we can see that for it to go from here to here, that was that, and the original amplitude was 20 centimeters. So 20 centimeters is equal to A. And what we want to know is if it's halved. So that means 20 centimeters was the original, and then it's going to go to 10 centimeters. And here we can see that it was 1 second. That's going to go to 0.5 seconds. So these are going to be your updated values. And how do we get this again? So let's do this a little bit more. So we know that, again, that period is the time for 1 full cycle. Period is 1 full cycle. Now, if T is equal to 0.2, then your cycle repeats every 0.2 seconds. Every 0.2 seconds. So that means that your peaks are going to be at 0, 0.2, and 0.4. Now, if we look at our graphs, that's just B here, because we can see that we still have your 20 centimeters, and you also have about half of them. So here, we can see that it's been just like halved. So it's going to be half of this. 20, 10, amplitude. You see our amplitude here. And so ignore that about amplitude. So now for our next question, 15. for our next, or our new amplitude here. Oh, sorry, what am I saying? 20 centimeters, T equals M over K. Well, this is actually for the wrong question. Yeah, I think that's more appropriate. So your amplitude for this graph, your amplitude has to be half of what it was here. And your new amplitude will be 10. Okay, so what you have here is your 2 pi m, so that's going to be equal to 2 pi 4m over k. So that's equal to 2t. So that means your t, it's going to be double. Therefore, your oscillations are going to be slower. Which does not match this one. That's going to be this one. Don't know why I put that. Okay, so a simple pendulum is set into simple harmonic motion. Which of the following graphs of the angular position theta of the pendulum as a function of time indicates the pendulum's oscillation has a period of 0.2 seconds and an amplitude of 0.1 rad. So we can see here we want to reach positive 10 and negative 10. And we want 0.2 as our period for a cycle repeat. So we want peaks at 0, 0.2, 0.4, and we can see that pretty much matches here. So now let's move on to our next question. So 16 and 17 refer to this. A block on a horizontal surface is attached to one end of the horizontal spring as shown in the figure. The other end is attached. The other end of the spring is attached to the wall. There is a negligible friction between the block and the surface, and a student pulls back and releases the block from various positions and records the amplitudes and the maximum speeds of the block. The student creates a graph of a maximum kinetic energy K max of the block as a function of amplitude A of the block's oscillation. Which of the following graphs best represent the expected shape of the graph? So what we're going to do here is we are going to have to examine what the variables are and find the proportional relationship between one another. And based off of what we are going to graph on each axis, that is what you're going to have to analyze algebraically of the curve. And this requires you being really careful about which one is going to be your x-axis and which one's going to be your y-axis, because your graph will look different depending on which variable you decide to isolate, which one you make the squared, which one you make the root, and if it's linearized, like when you do in labs and FRQs when you're linearizing data. So now what we can see here is that it's going to be B, and the reason is when you have your equations, you're going to have E is equal to 1/2 Ka squared for your total mechanical energy in simple harmonic motion, and this is from your spring potential energy, which is 1/2 kx squared, where x is equal to a. So that means all your energy equals to potential energy. So now what about our max kinetic energy? Your max kinetic energy is when your equilibrium point is x is equal to 0, so all your energy is equal to kinetic energy, because k max is equal to 1/2 Ka squared. When you do this, it's going to be your a. Now, what you can see here is that K max is going to be proportional to A squared. And what A squared is, when you have something that's squared, that is something that's parabolic, and we can see there's no negative, so that means that there's going to be no reflection. Therefore, we can say that this is going to start at your origin, it's going to curve up, and it's going to be parabolic. Now, which one of these is a quadratic? That was B, and that's why B was our